Hi, my name is Jim, and today's topic is series AC circuits. And what we're going to do is compare some of the theory to what you should have learned in DC circuits, and follow through from there. We're going to be using voltage divider and then a current times impedance check, just to make sure we didn't make any errors. So on this diagram here, I've not shown phasor notation, and sometimes I omit ohm symbols and volt symbols, and it's just to try to keep the diagram a little bit cleaner, because this is a pretty busy diagram. Start out in DC circuits, and this is where we'll begin, and we want the voltage VA out with respect to ground, and we would set that up in voltage divider, having in the numerator RB plus RC, and in the denominator would be R total, and that ratio is multiplied by the source voltage, which is 12 volts. So we're going to use that same technique in AC, except we have to deal with phase angles, which we didn't in DC, which makes it somewhat more complicated. So our starting circuit here is 12 volts at a reference angle of 0 degrees. That's usually what we start with, is 0 degrees. And I'm letting the source be 2 kilohertz. Sometimes you don't need to know that because you're just told a J value, and that's that. But I'm saying 2K, and that relates to an inductor value here of 143 millihenry. So if you were given the L in henries or millihenries or whatever, you would just use the inductive reactance formula to determine what the J value is, the imaginary value, because you'd have to be given the frequency. So I'm just giving you both here. We're starting out with 3 components in this, R1, R2, and L1, and what we want is the voltage across this guy. So setting this up in rectangular form is we have what we had in DC, basically 12 volts times the numerator, which would be 1.5K plus J 1.8K. And in the denominator we have the 2 reals being added together, the resistors, and again plus J 1.8K. Now, since we're going to be doing division, polar would be the easier thing to do. So what that would look like would be V out 1 equals 12 at 0, divided by Z1, which I'll define shortly, divided by Z total. So if I combine these 2 components, R2 and L1, into one component, which would be the same as adding RB and RC over here, I can get it in this form, and in polar form the division is very easy. So that's my first step, is to determine what the impedance that I named Z1, nothing special about that, and the other would be Z total, which would be including R1, the 2.2K. So to go about that, Z1 in rectangular form is 1.5K plus J 1.8K, and converting that to polar is the square root of the sum of the squares, and then the inverse tangent of the J value, positive J 1.8K, because this is an inductor, divided by the resistor here, because all we want here is Z1, and that comes out to give us in polar form 2.34K at 50.2 degrees. So we're about half done. Next, what we have to do is to find Z total. Okay, well, writing it out verbosely is we have 2.2K plus 1.5K, and then plus our J 1.8K for the inductor. So these are like terms, so the next thing I did was combine them, giving us a real of 3.7K plus J 1.8K again, and now I'm in position to convert Z total into polar form, getting ready for the division. So Z total equals the square root of the sum of the squares as before. Inverse tangent of 1.8K this time is over 3.7K, which is the total value of the real component, and in polar form that gives us 4.11K at 25 degrees ohms. Now, the thing to note here is that this circuit is more resistive than this circuit. Hence, the angle is closer to being real, as we'll see on the next sheet. So, as the resistance to imaginary ratio increases, the impedance will approach the real axis. So that's kind of a check value here, is that since we have more R in the circuit, is we would expect that angle to decrease, and it does. So plugging in the values here, Vout1 equals our source voltage, which is 12 at 0 degrees. In the numerator we have Z1 here, and in the denominator we have Z total. And multiplying 12 times 2.34K divided by 4.11K gives us a magnitude of 6.83 volts. And then to figure out the angles, we're taking 0 degrees. We're adding it to 50.2 degrees because we're multiplying. And then we're going to subtract from that a positive 25 degrees because we're dividing. And that gives us the angle for V out as being a positive 25.2 degrees volts. So let's check things out, and let's determine what the current flow is. And to do that, we'll have the voltage here, 12 at 0 divided by Z total. And that'll give us I. So we just have our polar forms here, and dividing 12 by 4.11K gives us 2.92 milliamperes, and then taking into account the currents, we have 0 minus a positive 25 degrees, and that gives us, 0, minus, and that gives us a negative 25 degrees. So the total current flowing in the circuit is 2.29 at negative 25 degrees. Now, if I push that current through Z1, I ought to get the same V out that I got before, and that's what I've done here in the green box. So I'm saying V out now equals I times Z1, which is the 2.92 at negative 25 degrees milliampere current flow, times the value of Z1, which is 2.34K at 50.2 degrees. And fortunately I get 6.832 volts at 25 degrees, which corresponds exactly to the number we got from the voltage divider. So I'm pretty satisfied with that. And if this were to be a capacitor, we'd have to be careful because we'd be dealing with negative J's. So you have to watch your signs when you do that, especially when you're subtracting the denominator, because you may be subtracting a negative number. Just remember the rules. You're subtracting, you change the sign to add, and then change the operation to add, and then change the sign of the subtrahend. Okay, so let's plot this and see how this looks. So we're going to do the hard thing first, and that's the current plot. And the reason is because we've calculated this, and it came out in polar notation. And if I'm going to plot it, unless I want to use a protractor and a ruler, I need to get it in rectangular form. So the way we do that is first we'll find the real component of the current, which would be our 2.92 times the cosine operator. So cosine is going to give us the real component, negative 25 milliamperes, and that comes out to be 2.65 milliamperes. Real, and that's the guy right there. Next we'll find the imaginary component of the current, so that's going to be 2.29 milliamperes times the sine of negative 25 degrees, and that gives us negative J, 1.23 milliamperes, which is somewhere down here. Then to just connect the dots, so to speak, and we end up intersecting here. So this will be our current phasor, which would be the 2.92 milliamperes, and the angle in here is negative 25 degrees. And do note that the current is in quadrant 4. Okay, so when you're plotting, just don't guess at it. Actually break it down into rectangular form and do it right. Cosine will give you the real, sine will give you imaginary. That's true whether you're dealing with inductive or capacitive circuits. Now let's do the next hard thing, and that's the voltage plot. So again, it came out in polar form to be 6.832 at 25.2 degrees. So first off, we'll find the real component, use the cosine operator again, which gives a real value of 6.18 volts. So I'll put that phasor there. And next I need the imaginary component of the output voltage, and that's going to be the sine, and that'll give us plus J 2.91 volts. So I'll put that phasor there, and then connecting the dots again and drawing the voltage phasor in polar form would give us a 6.832 that we had before, and in the angle there we see our 25.2 degrees. Now in these diagrams I don't have a grid per se, so these aren't necessarily going to be exactly in the right dimensions, but as long as you get the math and as long as you're working with paper that has a grid, you should be able to make pretty accurate plots. Now for the Z diagrams. Well, fortunately our Z's are in both Z1 and Z total are in rectangular form to begin with, so plotting those is kind of be easy. Z1 was the 1.5K plus J 1.8K, easy enough. 1.5K plus J 1.8K, connect the dots again, and then I get the sum total that we calculated in polar form before, so we could do the division easier, and that's 2.34 k ohms, and the angle that we had before was 50.2 degrees. So I plotted this in rectangular form, which we were given, didn't have to figure that out, and then just filled in the length of the impedance of Z1. So that's what that would look like. And then to do Z total, we also have that in polar form. If you recall, 3.7K was the sum of the two real components of resistors. Again, J 1.8, and connecting the dots gives us the total impedance of 4.11K, and the 25 degrees sitting between the real axis and the total impedance. So that's basically the form for finding any series circuit. Does not matter if it has an L or a C, how many R's. In a series circuit, what you need to know is that the I, the current, is the constant component. If you have an L and a C, remember they're opposites, so you're going to end up subtracting one J value from the other, and the largest absolute value will determine the flavor of the circuit. So we could go on to find our second output here. I haven't done it. Really would just kind of be a repeat. It would set up the same way, except if I wanted V out 2 in the numerator, the only thing I would have would be J 1.8K, and when you convert this into polar form for the division, just remember this is going to be 1.8K at an angle of positive 90 degrees ohms. So it's very straightforward to convert a pure imaginary into the polar form, and then as you can see, it's just a question of dividing that value by Z total here, which we would have to figure out as we did down here as 4.11 at 25 degrees ohms. So it would solve very similarly and give some different answers, of course. So that's about it for series circuits. Just make sure you understand when you do the plots that if there's an imaginary present, current and voltage are going to be opposite, and that's because you're dividing by the impedance. You're dividing the voltage by the impedance to get the current plot. And get it in rectangular form. Take your time and double check your work. Everything is good. So thanks for watching.